Good morning. So, we will just now we will just continue from the series what we are seeing, the transition metals. So, these are we have seen their role in biology, the molybdenum. Then we have seen how both molybdenum and tungsten do participate in biology, and little bit we have discussed about molybdenum, and so also with tungsten we will discuss about their coordination chemistry. So, how does this part of the inorganic chemistry can help us to understand the very complex biological reactions, because in case of the other congener of the group, that means the molybdenum, we have seen it is mostly dominated by the oxo transfer reaction, where the coordination chemistry is also mostly dominated by the formation of the oxo molybdenum complexes. So, this part of the reactions in biology, so these second group and second row and third row metal ions, the molybdenum and tungsten, when do participate, but they are not much abundant in the biological system. Only few examples are there where the tungsten center can play some important role in all these systems, and where these like molybdenum can move from an oxidation state of +4 to +5 to +6. That means, when we consider these, we can immediately think of that there is some electron transfer between these two oxidation state and also these two oxidation states. So, what we see that along with these oxo transfer reactions, which are mostly dominated by the reactivities with water, hydroxide ion, as well as with oxo anion. So, these groups basically following simple deprotonation, they can give rise to the hydroxide group or the oxido group, which can immediately go and bind to that of your tungsten center to give us a tungsten aquo bond initially, which can further go for deprotonation to give us tungsten hydroxide bond or tungsten oxo bond. And during all these transformations, sometimes we do not have any control over the oxidation state on the metal ion, whether the tungsten is in +4 oxidation state or +5 or +6 is very difficult to predict. So, we always, like that of our molybdenum part, we have seen that we rely on some of the useful spectroscopic techniques, such that if this particular one is in +5 oxidation state, and if we have one unpaired electron on that, so if that is in the 5d1 level, so we do expect to have some EPR responses. So, EPR response will immediately tell us, even in the solution in very dilute condition, where the concentration of this tungsten center is very less because it is surrounded by huge protein molecule, but the center which is having one unpaired electron in 5d level can show some response for its characteristic EPR signal. So, during this interconversion, when we move from aquo complex to an oxo complex, we basically go from a +4 to +5 to +6 oxidation state. So, along with oxo transfer reactions, what we expect that there is also some electron transfer reactions. Electron transfer reactions can also take place with that of the tungsten center. So, during that electron transfer we can have a single electron transfer, or we can straightaway a case where we can go for 2 electron transfer. So, we can have the catalytic processes which can be either a single electron transfer case or a double electron transfer case. So, very simple or very useful electron transfer reactions we can have, which we can get simple for this oxidation by air. That means, the oxygen dioxygen present in air can go for some of these transformations, but in the biological system we require, that means activating this dioxygen molecule is not so easy in the biological system. So, we there take the help of the water molecule attached to the tungsten center for these electron transfer reactions. Otherwise, in normal laboratory environment, we expect that some of these transformations are simply catalyzing by the presence of dioxygen molecule. So, that case the dioxygen is the most useful oxidizing agent or oxidant what can be acting on the substrate molecule. But in these cases, if this tungsten center is in +6 oxidation state, that means the hexavalent tungsten center which is attached to some oxo center is now the oxidant for all these biological transformations instead of the simple dioxygen molecule which is available in the air. So, in all these tungsten enzymes, slowly one after another we will discuss little bit on that, because we have discussed already the molybdenum enzymes in detail. So, is a very recent phenomenon. So, only during the last decade or last 15 years, people could isolate a number of tungsten containing enzymes. These we call it as tungsten enzymes in hyperthermophilic archaea. So, hyperthermophilic archaea means that these are very stable towards temperature. So, all these tungsten enzymes are thermally very much stable. So, they do not degrade in the range of say 100 and 105 degrees centigrade. They do not degrade, because otherwise we know that the biological systems what we can have in our body, which is only living till we have the corresponding temperature range of our body temperature, which is 37 degrees centigrade. But in case of these tungsten enzymes, they are very much stable till the temperature is reaching 100 degrees centigrade. So, these particular groups, they are known as the hyperthermophilic archaea, and these enzymes, the first one is of this category is the formate dehydrogenase. When the formate, the substrate is the formate anion, and which is involved in the redox transfer reactions. So, formate is sometimes getting oxidized to carbon dioxide molecule, what we have seen in case of molybdenum centers also, that means the molybdenum enzymes. Then another group of molecules which are very important, that means we are talking something which is nothing but the oxidoreductase family. That means the reversible oxidation and reduction reaction can take place, which is mediated by the ferredoxin molecule and which is acting on the substrate aldehyde. So, is a little bit complex arrangement where we have the redox enzyme. So, what we have in our hand is our redox enzyme. So, as soon as we have some redox enzyme in our hand, we obviously can think of that there should be some electron transfer from that enzyme part. But in case of this, we have that enzyme which is tungsten centered, and this tungsten center functioning as a redox enzyme, which is then under the category of oxidoreductase family, but which is coupled with some iron sulfur protein molecule, which we consider as the ferredoxin molecule. That means, at least we should have 2 iron centers connected to 2 sulfur groups. So, the basic unit what we can have, which is not a rubidoxin unit, but is a ferredoxin unit. So, at least a dimeric unit, if not a tetrameric one, which is the dimer of dimer thing. So, this ferredoxin molecule is basically can give rise to the electron to the system. So, the electron transfer is mediated through the ferredoxin molecule, and we have the aldehyde as our substrate. So, it is working on the aldehyde substrate mediated by the iron sulfur mediator, and tungsten is the corresponding catalytic site. And another group is that of your formaldehyde ferredoxin oxidoreductase. So, in one group it is acting on aldehyde, that means any other aldehyde, not that of the formaldehyde. So, it is aldehyde oxidoreductase, again from it is a thermophilic bacteria Archaea. So, this again belongs to the hyperthermophile. So, aldehyde oxidoreductase, it belongs to AOR family, but the other group which is very much specific on formaldehyde, that is why it is labeled as it is very much specific for the substrate which is formaldehyde, not any other aldehyde like acetaldehyde or any other group. So, this formaldehyde when acting on this particular tungsten enzyme, which is belongs to the class of again oxidoreductase and again ferredoxin mediated. So, this formaldehyde one, so we have aldehyde oxidoreductase, which is one family, the AOR family, and when we have the formaldehyde oxidoreductase, we get FOR family. So, FOR family is little bit different when we have the substrate as formaldehyde. So, this FOR family and AOR family, the reactivity wise or the source wise, sometimes the initial isolation was difficult, and once people have isolated that, then they went for the corresponding identification of the center as the tungsten one. So, in case of FOR family, we cannot replace this particular tungsten center. So, tungsten is very much needed for their reactivity, because the reactivity wise this group of enzymes, the tungsten enzymes, are very much similar to that of our molybdenum enzyme. So, if we can isolate some of these native enzymes from the biological sources, different biological parts we can take, and those biological sources can be checked whether we can substitute one particular metal center by the other. If the tungsten enzyme can be replaced by the molybdenum enzyme, because we want to check whether the tungsten is needed for their absolute reactivity for the corresponding transformation, or molybdenum can have a different catalytic role, or molybdenum can be more reactive. But in this particular one, where we truly speaking that they are the true tungsten enzymes, and this tungsten cannot be replaced by molybdenum, that means tungsten metal ion is very tightly bound to that particular center, and once tungsten is replaced by molybdenum, the reactivity for that particular center is also lost. But in some other cases, we can replace these molybdenum centers in different molybdenum enzymes. So, these are the bigger metal ion compared to the molybdenum one. This is a 4D element, this is a 5D element. So, 5D element can go and remove the molybdenum and take that particular position, but during that transfer we get basically a catalytically inactive species which is not active at all and which is not reacting on the substrate if the substrate is our formaldehyde or acetaldehyde. But some other cases, if it shows little bit of that reactivity, it shows very low activity analogues. So, the substitution of these, that means whether we can substitute a molybdenum center by a tungsten center, and we just basically check what is the effect for that substitution. So, metal ion substitution is a well known practice for this bioinorganic aspects of the different enzymes, because sometimes if we want to know the immediate coordination environment, and that particular environment do change because we are changing one particular size of the metal ion from molybdenum to a bigger one which is tungsten. So, definitely not only the coordination environment, but also the corresponding coordination number might change. So, in that particular case the reactivity pattern is also changing if we go for substitution of one metal center by the other. So, coordination number is also changing. And another important thing which we always should be careful in knowing that thing whenever we go for changing this thing is the corresponding redox electron transfer, that means the E0 values. The E0 values what we measure for one particular center for based on molybdenum to that of our tungsten. So, if that center is on molybdenum and this center is on tungsten, their E0 values are also different, which is well known to us that if we go down to a group, this particular center is weakly oxidizing compared to the other congeners in the 4D and 3D series, because in the 3D series we have the chromium on the left. So, whenever we have the chromium, which when we stabilize it as in terms of the corresponding oxo group, that means the chromate and dichromate anion, which is highly oxidizing compared to the corresponding molybdenum oxo unit, then which is again less oxidizing compared to that of our that tungsten center. So, we should compare always the E0 values what we get, because all these reactions are dependent on the corresponding E0 values and the corresponding thermodynamic stability of the corresponding substrate and the substrate which is giving the corresponding product. So, this low activity analog we basically get when we just simply change the corresponding center from that of tungsten to molybdenum or molybdenum to tungsten. So, is the essential element in all these enzymatic activity, and again we are talking that the hyperthermophilic archaea which thrive near 100 degrees centigrade. So, which basically stable and so can activity till we reach a temperature range of 100 degrees centigrade. And what I just now told you that the oxidized enzyme has at least one tungsten oxo unit having the tungsten center in hexavalent state, and one of them is that tungsten in the same oxidation state, but attached to a hydroxide unit. So, if we have the corresponding tungsten center, and if these two groups are attached to that corresponding terene unit, tungsto-terene unit, which are the sulfur groups. So, these are the sulfur groups. So, 4 coordination sites are already attached, and the size of this tungsten unit is little bit bigger. So, we have like that we are just covering a particular bigger ball or bigger sphere compared to the smaller one. So, 4 coordination positions are already taken up, and 2 of these positions are still vacant for the corresponding reactivity to the substrate or the other reagent what is coming out as oxo and hydroxide unit. So, if we see that this is one of them is oxo, so the next one can be the corresponding hydroxide unit. So, hexa coordination can be fulfilled around the tungsten center, and depending upon that it basically settle between this water, hydroxide and oxide unit to show the reactivity. And the terene unit, which is our source for these SS donor groups, the bidentate SS donor units, which is involved from the terene unit and which has important role in movement of electrons to and from the metal center in both the two cases. That means, in case of tungsten as well as in case of molybdenum, this basically the terene unit, that means the ligand part. So, these are our terene unit. If it is for tungsten, we call it as the tungsto-terene unit. If it is for molybdenum, we call it as a molybdo-terene unit. So, this terene unit from both the two sides can hold basically the tungsten side for its catalytic reactivity. So, this is the two these are the two cases. So, in the first case, which is the corresponding AOR family, the aldehyde ferredoxine oxidoreductase family, the first one. So, in the first case we have this particular aldehyde ferredoxine oxidoreductase family. So, you have this particular SS terene unit. So, is in dithiol unit. So, these two sulfur groups are the thiol sulfur units S minus S minus, and the backbone is little bit stabilized in the form of a double bond between these two carbon centers. So, it is basically a little bit of planar unit. So, this entire part what is there, this is the 2 plus 2 4 plus 5, this 5 membered ring is basically a planar unit with less distortion related to that of our carbon-carbon backbone, which is a double bonded one. Similarly, another group is also present on the right. So, which is also from the same terene unit, the terene bidentate sulfur-sulfur ligand. So, bidentate SS donor ligand. So, these are basically covering something, because this basically giving some important coordination geometry which we are not getting unlike our first transition series elements, because whenever we find in case of iron, nickel, cobalt etc., all if the metal center is present over there, and if we have one donor group from here, another donor group from here, another donor group here and another donor group here. So, for the 3D elements and which is not biologically connected. So, these are non-biological donor groups. So, non-biological donor groups, they basically prefer for again this, if this particular individual unit, that means if this particular ring, whatever ring it is, it can be 5 membered ring or it can be 6 membered ring, but if this part is a planar one, and depending upon the nature of the metal center, we can have the square planar environment, or if this particular 5 membered ring or 6 membered ring is perpendicular to the other ring, we get a tetrahedral geometry, but basically it is settling between either a tetrahedral geometry or a square planar geometry. So, when two of these ligands are attached, so we go for the attachment of the 5th and 6th groups, but in this particular case the attachment of the 5th and 6th, which is also true for the iron center which is present in our hemoglobin and the myoglobin molecule. So, with one of these group will come from above the square plane and another will from below the square plane, making a corresponding octahedral geometry. So, this octahedral geometry what we sometimes draw in the form of the corresponding trigonal plane, because this is one of such trigonal plane and below we have another. So, if we just look at the corresponding C3 axis, so viewing along the C3 axis, so which is the threefold axis C3 axis, we get some arrangement where we have one trigonal plane. So, if we can move these two trigonal planes, these are the staggered orientation. In typical octahedral geometry, these two planes are in staggered orientation, but this particular one can move from here to here and you can get a corresponding eclipsed orientation. So, between these eclipsed orientation we can have a corresponding geometry which is a prism geometry. So, we can have a corresponding hexagonal arrangement where the metal center, that means tungsten, is sitting over there and 6 positions, 6 coordination sites are available. 6 coordination sites are available for binding. So, we can have any kind of distortion, particularly when we have the bigger metal ion present, we can have huge distortion because we do not have any control or any ligand to ligand or donor atom interaction between these, which is very much true for smaller metal ion like nickel, iron or cobalt, where you can have the corresponding interaction between these things and we do not get a huge distortion in the coordination site. But in this particular case, so we have the 6 coordination site, these two are fixed, bidentate fragments are fixed, but these two are monodentate one. So, we can have a corresponding geometry where you find that these dotted coordination sites, this is one of these threefold axis what we have seen just now. This is one threefold axis and including OSS, this is another threefold axis. So, this threefold axis and another threefold axis, if we consider these two are the two planes, the C3 planes. So, one C3 plane and another C3 plane, they can adjust themselves depending upon the corresponding size of the metal center based on the corresponding oxidation state. That means, whether our tungsten is in +4, +5 or +6 oxidation state, we can have these typical arrangements. So, these particular enzymes basically fall into 3 groups and crystal structures of these 3 groups have been identified so far, and people have identified the corresponding coordination from this terene unit, the tungsto-terene units, 2 such tungsto-terene units fulfilling this particular site, and the other 2 sites are occupied by oxido and hydroxido groups. So, this particular one, this AOR family, the aldehyde ferredoxin and formaldehyde ferredoxin oxidoreductases. So, AOR family and FOR family, these are the 2 families and they are basically identified from Pyrococcus furiosus and is abbreviated as PF, Pyrococcus furiosus PF. So, this is the biological name of the origin for this particular enzyme. So, crystal structure basically tells us that what type of distortions we can have, because this particular geometry is not at all an octahedral geometry, but which is in a different form, and between the catalytic turnover basically the adjustment of the coordination center can also take place. And when this particular center is acting on aldehyde, so definitely we expect that this is basically the corresponding oxidation reaction, and that oxidation reaction the corresponding aldehydes are getting oxidized. So, these aldehydes what we can have, so in AOR family, the aldehyde oxidoreductase family, where R is basically the corresponding methyl group, we get the acetaldehyde. So, when it is acting on acetaldehyde, we get RCO2H, means the corresponding carboxylic acid formation. So, this we all know from the knowledge of organic chemistry that this is well known oxidation reaction. Even if you have some benzaldehyde in our hand, the bottles of benzaldehyde in the laboratory can be oxidized very easily by the dioxygen present in air. So, dioxygen can be a very good oxidizing agent for all aldehyde like substrate, particularly the benzaldehyde and acetaldehyde. And this particular conversion of this acetaldehyde to acetic acid, what we have seen in case of the corresponding molybdenum based enzymes, where we can take care of the corresponding oxidation of ethanol to acetaldehyde. So, this particular conversion, so this is an oxidation reaction. So, some electron flow can take place in the reverse direction. So, in the reverse direction, the electron can go for the corresponding transfer. That means, once we oxidize the aldehyde to carboxylic acids, the reducing equivalents are being transferred to a 4 iron 4 sulfur ferredoxin. So far we have seen that this is dependent on iron sulfur ferredoxin molecules, and this ferredoxin is now our Fe4 unit. So, 4 sulfur 4 iron ferredoxin molecule, which is we all know is a basically a cube type molecule, where all the alternate corners are occupied by iron and sulfur groups. So, if these are the iron, so other alternative corners are occupied by sulfur groups. So, in this particular case, so this ferredoxin molecule, the iron centers are settling between +3 to +2 oxidation states, that means between the ferrous and ferric oxidation state. So, depending upon the number of electron transfer which is being taken up for this particular oxidation reaction, whether we are talking about some electron transfer which is single electron transfer or a double electron transfer, we should rely on a 2 iron ferredoxin molecule or a 4 iron ferredoxin molecule, because sometimes we find that though you can have 4 iron centers present and all the 4 iron centers can be reduced to +2, or all the 4 iron centers can be oxidized to +3. So, you can extract out if it goes from a typically reduced form where all the iron centers are present in +2 oxidation state to a system where all the iron centers are oxidized to +3 oxidation state, we expect to get 4 electron transfer for this particular system. But in most cases we get one particular ferredoxin molecule which can provide us 2 electron transfer. So, ferredoxin molecule which is based on 4 iron center, which can go for 2 electron transfer. So, either it can be oxidized by 2 electron or it can be reduced by 2 electron. So, which is very much unlike for 2 iron ferredoxin system, because in 2 iron ferredoxin system what we have seen just now, that we have 2 iron system and these two can settle between the corresponding oxidation states, and here also it can initially go for a single electron transfer. That means, already the system is in mixed oxidized form, that means one center is in +2 and another center is +3. So, it can be reduced for this iron or it can be oxidized for the second iron. So, when this we get for this corresponding oxidation of the aldehyde to acid corresponding acid, this reducing equivalent being transferred to the 4 iron 4 sulfur ferredoxin. So, whatever reducing equivalent we can generate from this particular oxidation reaction, that is getting transferred to the ferredoxin molecule. So, this reduced form of the ferredoxin molecule then take part in the corresponding catalytic cycle to the next step. And this is one particular aldehyde, or in the general form it is possible for all other aldehyde molecules starting from the acetaldehyde, but for formate, this formate dehydrogenase family is little bit different only towards this particular coordination of OH, because this particular one from the cysteine sulfur or selenocysteine selenium, it can be attached to this particular tungsten site, and since these corresponding donor atoms are bigger in size, if it is sulfur or if it is selenium, close to another bigger unit which is our tungsten unit. So, very easily from the determination of the crystal structure, we can identify the nature of these donor groups attached to the tungsten unit. And that also, when a bigger unit is attached to the tungsten site, though tungsten is in the hexavalent state, which is the smallest possible among the all three oxidation states available for the tungsten, but this basically this bigger donor atom can also distort the coordination environment around this tungsten site. So, this coordination center which is attached to the oxygen and which is attached to the sulfur or selenium are different. So, that is why the reactivity pattern for formate dehydrogenase is also little bit different compared to that of your normal other general aldehyde. So, this aldehyde oxidoreductase, so they can reduce or oxidize these two fragments. So, one is the corresponding aldehyde. So, they can also work on aliphatic and aromatic aldehydes. So, it is very interesting to note that in the biological systems, when certain system has been identified, and that system when we identify as it is working on some aliphatic unit. So, this particular aliphatic group is available. So, this aliphatic aldehyde is getting oxidized by AOR family of tungsten enzyme. We expect that whether that particular center can also be operating on the aromatic aldehydes as well, but the biological substrate what is coming out from the biological system is the aliphatic substrate. So, if people can isolate that particular enzyme, so AOR family of enzymes, if we can isolate that particular enzyme can be tested for their reactivity on some aromatic aldehyde like benzaldehyde or any other aldehyde, because the corresponding enzyme pocket is very important to hold the substrate, because some cavities should always be there which can take up the corresponding aldehyde close to that of our tungsten center, which is our catalytic site. And in this particular case, if the aliphatic aldehyde is of biological origin and aromatic aldehydes are of synthetic origin, they show equal type of catalytic efficiency towards these two aldehydes. So, they can also show good efficiency towards other substrates which are our common amino acids, such as when it can act on acetaldehyde. So, acetaldehyde which we are getting from alanine, alanine is this one. So, it can basically go for the corresponding transformation. So, alanine can be transferred to acetaldehyde, and that acetaldehyde can be utilized for substrate for AOR family of molecules reacting on it to giving rise to corresponding acid function. Then isovaleraldehyde. So, if we have the valine as the corresponding amino acid, so that valine unit can be converted to its corresponding aldehyde, which is isovaleraldehyde. Isovaleraldehyde is this molecule. So, isovaleraldehyde can also be a good substrate. So, not only acetaldehyde which we identified, so a good range of other aldehyde molecules can be tested for this particular reactivity. That means, tungsten can be a very good catalytic site. So, that also tempted us to discover some good catalyst which can be based on tungsten center. So, tungsten based catalysts can be developed with these informations. Then also this corresponding other aldehyde where you have the corresponding phenylacetaldehyde. So, it is not directly a benzaldehyde, because benzaldehyde, the corresponding aldehyde function is directly attached to the aromatic carbon of the benzene ring. But if we have a C6H5 CH2CHO type of acetaldehyde, that means the phenylacetaldehyde, which has a biological origin also, it is coming from the amino acid phenylalanine from the deamination reaction, because all these things can go for the corresponding deamination reaction like that of our alanine, because we can go for the corresponding keto function over here, and that when goes for the corresponding oxidation, leaving behind us the corresponding decarboxylation for the CO2 unit. So, this unit goes as CO2 and this part is oxidized to acetaldehyde. So, that acetaldehyde can be utilized for substrate for this enzymatic activity. So, all these molecules which are directly or indirectly supplying some aldehyde based substrates. So, these aldehyde based substrates can be tested for their reactivity, which is a very useful 2 electron redox process. That means, our acetaldehyde molecule in presence of one molecule of water can be oxidized to acetic acid with the liberation of 3 protons and 2 electrons. So, this liberation of these protons and electrons can take part in basically some of our well known fact of that electropotic equilibrium, that whenever we have that electron transfer sidewise, you can have the corresponding proton transfer from the system, and these 2 electrons are basically taken up by the oxidized form of the ferredoxin molecule. When we have the 4 iron ferredoxin molecule, where the oxidized form of this is giving us that the iron centers in the +3 oxidation state, and those +3 oxidized state of the iron centers can take up these 2 electrons and reduced back to the reduced form of the 4 iron ferredoxin molecule. And these protons are attached to some of the other sites where we have some basic sites can also be available from there, and those sites can be attached with these proton liberated from these reaction. So, basically what we find this basically this particular transformation what we are seeing there, that is basically a 2 electron transfer reaction, and these 2 electron transfer reactions already we have seen, we have thought of that the individual ferredoxin center can take up those 2 electrons to change from one form of the ferredoxin, that means ferredoxin in the oxidized form and ferredoxin in the reduced form. So, in the catalytic cycle, which direction this particular reaction can go, whether from the carboxylic acid to aldehyde or aldehyde to carboxylic acid, that definitely depends on the oxidation state, that means the oxidized form of the tungsten center, as well as the state of the ferredoxin, that means whether the available ferredoxin molecules are in the reduced form or the oxidized form. So, knowing this particular type of oxidation based on tungsten, then another group of molecule which we immediately feel that once we are able to oxidize that aldehyde, that means aldehyde oxidoreductase family, which is acting on the aldehyde molecules, what we are producing is the corresponding carboxylic acid. So, these carboxylic acids, if they can be reduced back to the aldehyde, we get another group of or another family of corresponding enzymes. Those enzymes are known as the corresponding carboxylic acid reductase. So, along with AOR family, we get another family which is CAR family, carboxylic acid reductase family, and biologically also they can be available from some of the acetogenic Clostridia. So, acetogenic Clostridia is the corresponding acetyl function which we can generate, that means the acetogenic bacteria or the acetogenic corresponding Clostridia can develop to get some of these groups as the corresponding acetyl function, which can be obtained from the corresponding reduction of the carboxylic acid function. This was first identified and its ability to catalyze the reduction of non-activated carboxylic acid. So, if we have some group which is, we know that the R group, and this R group is attached to the corresponding carboxylic function, and the reactivity for this carboxylic function, that means R is there and that is going for the corresponding aldehyde function. So, this particular reactivity, that means what we are taking away, we are taking away this particular oxygen atom from this particular unit. So, the removal of this particular oxygen. So, this particular catalytic activity is very much dependent on how we have the corresponding carboxylate function is activated. That means, if we just go for R as the phenyl ring, R is attached to some benzene ring, which is also attached to C double bond OH function. So, what type of reaction based on these enzymes we get, and if we get a different reactivity pattern for this reaction, we immediately can say that this phenyl function is basically deactivating the carboxylate function. So, which is deactivating the carboxylate function for this sort of reaction. Whereas, the R group, if they are activating the carboxylate function for the smooth transfer from carboxylic unit to the corresponding aldehyde function, we consider that this particular R function has some role to play for this particular reaction. So, depending upon of all these substrates, whether this particular substrate, which I already told you that this particular substrate, if it is R is equal to methyl function, and if it is a biological origin, so definitely this has some catalytic function and catalytic rate, and we can measure the corresponding rate of the catalysis based on that particular substrate which is biologically available for that particular enzyme. But if we just move for some artificial substrate which we are not getting from the enzymatic system, so this particular artificial substrate can be tested for the role of this R function for this catalytic action, and whether this particular enzyme, whatever tungsten enzyme we are utilizing this for this reaction, can be utilized for other biochemical transformations or biocatalytic transformations where the substrate is added or substrate is utilized from outside. So, during this particular conversions, what already we discussed, that this typical oxidation reaction or the reduction reactions from the corresponding carboxylic acid to aldehyde is definitely related to some redox couple, which can be measured very nicely by polarographic measurement or cyclic voltammetric or any other amperometric measurements for their E0 values. So, this acetaldehyde acid redox couple has a very low E0 value, which is minus 580 millivolt. So, minus 580 millivolt is a quite negative redox potential compared to other standard reference electrode. If we have a reference electrode like normal hydrogen electrode or saturated calomel electrode or any other standard reference electrode, we just consider this, and this as minus 580 millivolt is reported with respect to normal hydrogen electrode. So, how useful this particular potential is in finding or in identifying the corresponding redox couple for these transformation we can think. So, if this potential is very small, the corresponding aldehyde oxidation, what we have seen that if it we have in a bottle or if it is in a test tube, is very easily oxidized by the oxidation from the dioxygen present in the air. That means, no catalyst is required, nothing is required, only the dioxygen present in air can oxidize nicely this aldehyde to carboxylic acid, and the extra oxygen what is there going to attach the aldehyde function is coming from the dioxygen molecule. And this particular case, that this one, that means the dioxygen which is functioning as an oxidizing agent. So, E0 value for the dioxygen is much more positive compared to the corresponding the reduction potential for the corresponding acid aldehyde conversion. So, once we find the corresponding E0 value, so the if it is with respect to the NHE, the E0 value we can, if we know, and this E0 value can be correlated with the delta G0 value, that means the free energy change, and that free energy change can also be correlated with the corresponding minus RT natural logarithm of k. So, once we find this E0 value for the any transformation, we can find out the corresponding delta G0 value and the corresponding k value. So, once we determine the equilibrium constant, this k is nothing but the equilibrium constant. Once we determine the equilibrium constant for the reaction, we immediately know the corresponding reaction, whether it is a enzymatic reaction or non-enzymatic reaction, how much facile the reaction is for transferring one side to the other. So, therefore, this aldehyde oxidation is much more thermodynamically favorable. So, immediately by determining the corresponding E0 value from this reaction, we can talk about the corresponding driving force, the thermodynamic driving force for this particular reaction in terms of the corresponding comparison with the equilibrium constant, and we can comment on that this particular reaction, if the k value is very high, that means the equilibrium constant is very high, it immediately goes from one side to the other due to that particular catalytic transformation. But we can have some kinetic barrier related to this particular reaction, and the enzyme environment, whatever enzyme environment we can have. So, if we have the typical enzyme environment, and if it is in the huge polypeptide chain, and this polypeptide chain, and within that polypeptide chain we have the tungsten unit present, and we are thinking of some electron in and electron out business. So, electron is entering or electron is leaving from the system for the catalytic reaction, and the E0 value we have determined for that particular transfer, and the corresponding kinetic barrier we should also determine that the rate of that electron transfer. So, the rate of the electron transfer is also important. So, if we are able to overcome the corresponding kinetic barrier utilizing this enzyme, we also get a very fast reaction based on this particular tungsten center. So, this determination of E0 values, because we can have some measurement, some instruments are also available. So, those instruments like the cyclic voltmeter. So, cyclic voltmeter can immediately determine the corresponding E0 value for this enzymatic. So, electrochemistry for these enzymes is very important. So, our electrochemistry of the enzymes are very important, and this electrochemistry on the electrode surface what we do, and those electrode surface and which is sometime bound with the immobilized enzyme. So, this enzyme can be bound to the electrode surface. So, we have this electrode surface, and on that electrode surface we basically go for the immobilization of the enzymes and we have to see the corresponding substrate what is getting oxidized. That means, you can have the corresponding substrate as the corresponding aldehyde or the acid. So, all these things basically can comment on whether we have a very useful enzyme based on tungsten and whether we have a very useful enzyme which is based on the molybdenum. So, these particular things can basically utilized for the comparison of this molybdenum versus tungsten. So, next day we will just see whether this particular tungsten enzyme can also be useful some other system, and in our future classes we will just slowly correlate that whether the chromium can have some biological role as well as the vanadium in this particular environment, because we have seen that all these 4 metal ions can give rise to the corresponding oxo functions very easily. Okay, thank you.